In this short tutorial, we are going to model a cylinder which is extended in the z direction. We will create a crack on the cylinder while fixing the bottom in all three directions. The top is going to fixed in the x and y direction, while it is going to be elongated in the z direction. We will see that after elongating our cylinder, we will stop the actual movement of the top. However, we will see a continuous increment in the crack without actually moving the top. We will use the following material properties and a tetrahedral mesh. In the original paper, we published a hexahedral brick type element. However, in this version, both tetrahedral mesh with one integration point and the hexahedral mesh with 8 integration point is available. Let's open ABAQUS and start a new standard explicit model. Always make sure that your work directory is set correctly, then save your model. Let's name it cracked cylinder. Press enter and then start to create the part. We will name the first part cylinder, which should be created by extrusion. The approximate size will be 5. It is deformable. Let's click continue. Here we will draw 2 circles, one with the radius of 0.9, while the second one will have a radius of 1. Terminate the command by pressing on the small red X and then click done. The depth of the extrusion is going to be 2. Click OK. Now we will create the crack itself. Let's name it crack. It should be also a 3-dimensional object which is created by extrusion. The first point should be at minus 0.2, 0 in the y direction. Then we will give the crack a very small height, and that is 0.0001. The third point should be the same as the first, just on the opposite side, which is going to be 0.20. The other side is minus 0.0001, and let's close our polygon. Click on the X and click done, and give the same kind of 2 as its depth. Now we have the 2 parts. Let's go to the assembly module to actually subtract the crack from the cylinder. Let's create an assembly by highlighting both crack and cylinder. Use a dependent mesh and click OK. We can see that the actual crack shape is oriented in a different direction as we would want to. Therefore, we are going to rotate it first. Let's select the crack, click done. First, we would need to add a vector around the rotation, which is going to be created. This vector is going to be along the x-axis. Therefore, the first point can be 0, 0, 0. The second point should be 1, 0, 0. And the angle is going to be 90 degrees as it is shown here. Click enter. We can observe that our crack geometry is rotated as we wanted. Click OK to accept the actual modifications. Now we are going to move that crack onto the middle of our cylinder. To do this, click on the move part button, select your crack, click done. The first point where we are going to start the movement should be at 0, 0, 0, and then we are going to move our crack to 0, 0, and 1 in the Z direction. Let's see if it is moved into the good place. Yes, it's good. Let's click OK to accept it. Now we should subtract the two parts. So click Merge Cut Instances. The new part should be named Cracked Cylinder. It should be a cut. We will not delete but suppress the original elements, the original instances. Click Continue. First, you need to select one and one part only, from which we're going to subtract the second one. Now ABAQUS doesn't ask our confirmation, just steps to the second question, which is what kind of instance do we want to subtract from the cylinder. We will highlight the crack, we will click done, and we can see that the crack itself was subtracted from the cylinder. Now we can go back to the property module, switch the part to the cracked cylinder, and save the model by clicking Ctrl S. Let's rotate the cylinder to see how does it look like. Great. Now let's create our material model for the UMAT material. For this we will add a solution dependent variable which has 26 state variables, then add a user defined material with the first constant is 1 times 10 on the power minus 11 and some kind of Poisson's ratio which should be 0.3. Let's click OK. To create a section which we can then assign to the actual part, click on Create Section, then type sample as the name of the section. It makes no difference. Make sure that the material is the UMAT material which we have created. Click OK, and then assign this section to our geometry. Let's name this set as cracked cylinder. Highlight the actual part, click done, and then make sure that the section which we are assigning to the part is the sample section which we have created earlier. Perfect. Now we can move on to the next module, which is going to be the assembly again. Here we will create a reference point to be able to record and measure all the reaction forces from the actual top. The first thing we should do is to create an arbitrary node with a coordinate of 0, 0, 2.5. We can see that it is created on top of our cylinder. Go to Tools, Reference Point, and just click on the node to create our reference point. It is important because this way we can create a set by clicking on the module tree, clicking right, and create a set. Let's name it RP as reaction point. Click Continue, select the created reaction point, click Done. We can do the same first for the top. Make sure you select the actual surface and not the edges. Click Done, and we can do the same for the bottom. Let's name it bottom. rotate it a bit, close this window and select, click continue and select the actual surface. Good. Now we have our sets. We can move on to the next module, which is going to be the step module, where we define the actual analysis steps. First, create a new analysis, which should be a static general analysis. The name can be step 1. By clicking continue, we can set the time period which we want to have for this module. As we saw in the introduction, we will have 2 for the time period, where the increments are going to be fixed. Let's have 200 time steps when one time step is 0.01. This will give us 2 at the very end. Let's click continue and let's see what kind of output do we want from this model. First of all, we will need all the displacement from the nodes, and then we will record the reaction point from only one set, which is going to be the reaction point, and the reaction forces which we will ask for. In this case, click OK and dismiss the window and save the model. Let's go to the interaction module. Here we will create the constraint between the reaction point and the top, so that the top will be able to move in the Z direction, same as we want the reaction point. To this, click create a constraint. This will be an equation constraint. First, name our top, set the 3rd degree of freedom, so the translation in the Z direction. This will be coupled with the translation of the reaction point, set 1 and -1 for the equation constants. Click continue. We will see that it will highlight for us the actual area which we connected to the reaction point itself. By saving the model, we can move on to the loads, where we will create our boundary conditions. First, create a boundary condition, which will be a displacement rotation boundary condition. This is going to be a fixed boundary condition on the bottom. Click continue, search for the bottom in the right bottom corner, and select the bottom set. Select 1, select U1, U2 and U3 as the 1st, 2nd and 3rd degree of freedom, the translation in the X, Y and Z direction. Set it to 0 to constrain them. Then let's do the same for the top. However, here we only will constrain the displacement in the 1st and the 2nd direction, so X and Y. Let's leave it on 0, click OK, and then we will add our displacement in the Z direction. Let's name it load. This will be a displacement boundary condition. This will be applied on the reaction force in the Z direction. Let's set 1 as the amplitude, and let's create a table where we will give the actual values of the displacement. At 0, the displacement is going to be 0. At 0.5, the displacement will increase up to 0.005, and at 2, we will keep the same kind of 0.005 displacement. So between 0.5 and 2, our reaction point, thus the actual surface, will not move anymore. Make sure that the amplitude is set to the table. If everything is good, Let's click OK. Now we can move to the mesh. Make sure that the mesh is defined on the part, which is the cracked cylinder. Here we can see that the part is actually orange, which means that ABAQUS can't really mesh it. Therefore, we're going to change the element type from the hexahedral, so the brick element, to the tetrahedral element. Here we can leave everything on default. We can change the type of the element by clicking dismiss and highlighting the part by clicking done. As the UEL in our case has only one integration point, then this element is going to be linear. Let's click OK, and let's define some kind of average mesh size. This should be 0.1. Click OK, we will see the original seeds, and by clicking mesh the part and clicking yes, we will see that it generates a fairly rough mesh. However, we already have 9,000 elements, and if you have time, you can decrease this value and see what is the effect of the increasing mesh density. However, for this short tutorial, we will keep this kind of very rough mesh here. Move on to the job module. Let's create the job. Let's name it cracked cylinder. Click continue. Here you can click OK. Go to the job manager and write an input file. Let's go to Matlab. Here we will use a Matlab file which I have created to actually transform the original ABAQUS created input file to an input file which uses the UEL itself. Let's go back to ABAQUS and let's start typing ABAQUS to face field UEL 3D, as there is a two-dimensional version in the second tutorial on my webpage. In parentheses, let's write the name of the input file, which is cracked cylinder.inp, comma, and here we would need to add the material parameters, which is first going to be the Young modulus 400, then the Poisson's ratio 0.3. Here we can add a stability parameter which will make no difference, however it stabilizes the numerical simulation. Details can be found in the article. And then the length scale parameter of the diffuse crack, which is going to be 0.2, and the surface, the fracture surface energy, which now is going to be 1,000. So finish the parenthesis and click enter. Now the script will create a new input file and we'll copy the original Fortran file by increasing the number of elements in it. Yes, it is done. So we have the new input file and the Fortran file. Let's go back to ABAQUS, create a new job. However, now select the input file which we have created with Matlab. Click continue. In the general tab, select the user's subroutine and the Fortran file which we want to. Click OK and submit the job. After we see that the status has changed to completed, we can go to visualize the results. First, we will clean the viewport by selecting only the UMAT element, click replace, close the window. Let's rotate our cylinder to see the actual crack. Let's change the common options that the deformation should be 0. We only want to see the featured edges. Click OK. Now we see our crack. If we want to see the actual fracture itself, let's see the 25th solution dependent variable. It's clear that the whole cylinder is fractured. We can visualize it using an isosurface. Let's change to isosurface. Let's set the limit from 0.93 to the maximum. Let's click OK. We will see the propagation which takes place quite nicely from here. Yes. Tac tac. Yes. It is complete. Now let's see the reaction forces on the reference point with its displacement. Let's change to unit model. Let's visualize the displacement in the z direction and the reaction force in the z direction. Let's select a node set which is going to be the reference point, and let's click plot. We will see that the actual displacement of the top stopped at 0.5. However, the crack continued to propagate. Therefore, if we want to see the reaction force as a function of the top displacement, click on operate on XY data, search for the combine option, click once on this. The first variable is going to be the displacement, the second is the reaction force. Click on plot expression, click cancel, and we can see that after we reach our maximum, the crack starts to open. Even if we stop the actual loading process, the crack will open up. What would be interesting to see is to play with the actual size of the time step during the loading process, and of course the density of the finite element mesh. However, this is going to be a homework option because this image terminates this tutorial. To sum up what we did, we created a cylinder with a cracked side. We extended it in the y direction. We saw a beautiful symmetric crack opening. We increased the displacement on the top until a certain time, then left the top there. However, we saw that the crack propagated in an unstable way. Thus, the static method actually calculated the crack opening without actual loading. For this model, we used the new tetrahedral element, and that's it. See you next time.